Hi, my name is Joseph Zhang. I'd like to briefly talk about the major steps you should take when you try to set up a Schism 3D. So I will use the Pacific domain as an illustration. Okay, so here is the brief outline of the course. Um, so I will first give you a very high-level introduction, assuming that you don't have lots of knowledge about the schism, and I will introduce you to some key concepts, especially for setting up a schism 3D. And then I assume that they are, we will follow a fixed workflow from mesh generation all the way to the post-processing. So we'll not talk about how to tune the model in detail. So I will then give you a quick tour about how we generated the Pacific grid using SMS, and I will describe some of the concepts there and the key points and the key steps there. And then I will show you how we do the pre-processing, preparing all the Schism 3D inputs for this particular mesh. And lastly, I will talk about the post-processing and visualization. So let's start from the introduction. Okay, so this is a typical workflow for setting up the schism. Okay, you start from mesh generation, right? And then immediately after mesh generation, you need to try to set up the 2D model, and specifically, you don't really need to set up the entire model inputs. Instead, you turn on the preprocessor inside the schism to check the mesh integrity. Okay, so this will save you lots of time. And after you pass this step, if you don't pass this step, you need to go back to mesh generation and modify your mesh. And after you pass this preprocessor step, then you need to go. It's a good idea to set up a 2D model. Make sure that the results make sense, and then you proceed to the 3D model. And of course, if you find any specific issues related to the 3D model, then you probably need to go back to the mesh generation. Okay, so let's go through the very first step, how to compile the code. And to compile Schism, you need some basic libraries. Okay, so these libraries include Fortran and C compilers. Of course, you need that. You need both serial and parallel versions. Okay, and you also need the LetCDF library. We use newer libraries, version 4.3 and above. The reason is that starting from 4.3, the LetCDF library is split into two libraries, one for C and another for Fortran. That's the one we use. And your system needs to have some basic Python library and also Perl. Okay. And this is optional, but we recommend that you use GitHub to clone the Schism source code to your local system, right? And then, so this way, later on, after you compile, after a while, you can actually use the executable to query the code version, or so-called hash. And for pre-processing, we like to use this ACE tool. So this is a Linux-based tool. It's very efficient, and a lot of features are specifically written for Schism. So we highly recommend this tool. So even though this is optional, but we really suggest that you install the ACE tools on your local system, especially GREdit. It's a great editor. So first, you clone your source code, Schism source code from the GitHub, right? So this is a clone command. So this is relatively straightforward. And then you try to compile the code. There are two ways to compile the Schism. One is the preferred way, which is a CMake, because we are starting to couple with many other models and libraries. So CMake makes things more streamlined. So this is a preferred approach. So basically inside the CMake, you create top level directory called build. Okay, and in addition, after you clone the SCHISM source code, you should see a directory called CMake. Inside, you'll find two files that you will need to for the CMake process. The first one is called schism.local.build. So this is a file where you switch on and off optional modules for Schism. So for Pacific project, we only need the precipitation and evaporation module. So that's the only thing you should show them. And the second make file is basically to define some basic paths, like the where C compiler, Fortran compiler, CDF libraries are on your cluster. So to prepare this file, you need to copy a similar setup, some template. You can find lots of templates in this CMake directory. So for example, we have a template for the Orion. It's actually working copy for Orion. So you can copy from that and make some modifications. And after that, you go back to the build directory and blow everything away. Okay, I always like to, this like a make clean. And then you issue this CMake command using the two files I just talked about as a cache file. The first one is a module. The second one is basically the system path. And this, of course, you do the CMake inside the source directory. And after that, this is successful, then you use make. You can even use manual make. So let me show you the process on our system. Okay. So now I'm on our home cluster, Cyclone. So this is a build directory I was talking about, right? Above that, you see the CMake directory here and the make directory here. So first of all, blow everything away. So we are on Hurricane. So basically, you go in here and build. Make sure you turn on and off modules. So right now we turned on the Faber module. We don't need that, so just turn it off. Okay. So, and if you want to turn the like a Pacific project, you want to turn this precipitation evaporation module on. So just do that. And another one, it's already prepared, Whirlwind. So that's the one shows defines all the basic paths like a C, Fortran and C compiler paths, as the CDF, C, and the Fortran libraries where they are, and also the compiler flags. So we don't need to change that. So now we just issue the CMake command. This is the CMake command. So change this cluster to the cluster name here. Okay. And one thing, CMake will is now basically looking for all those paths. And one thing you can do is preview the final executable name. You can see that we turn down precipitation evaporation modules. TVD VL is always there, so you cannot turn it off. So now we just do parallel make. That's it. Another benefit of using CMake is that it will automatically create lots of nice libraries like the domain decomposition library, Parmetes and Metis, and also the Hydro core library. Okay, so you can use those libraries in other coupled applications directly. Okay, so now it's done. So you can see all the executable inside the bin directory. Okay, and also you have a library directory where you have some compiled libraries there also included as well. So let's go back here. So that's the CMake part. So now let's look at the second approach to make. That's the glue make. That's the one we still support, but again, the preferred approach now is a CMake. So in this glue make approach, similarly you prepare two files. One is the make dev local. That's the one equivalent to the system specific CMake files. That's where you define the path of let's say df, etc. Okay, those kind of environmental variables. And when you clone from the GitHub, you don't see this file. You need to either link or copy existing template to this file and make some modification to suit your local system. And also you need to turn on and off optional modules in this file called include modules. And then you cd into the source directory, make clean and make. That's it. So now let's look at the some details of the